So, as I showed you in the previous lecture, this is die vacancy formation equation or reaction. So, there is one vacancy here somewhere isolated, another vacancy over here isolated, it has 6 broken bonds over here, it has 6 broken bonds over here, and let us say by a reaction it forms a die vacancy. So, there is a bonding between these two. Now, here we see there is you needed 12 broken bonds. So, the energy required is proportional to 12 EBR. Here we have 10 broken bonds. So, there are only 10, it is proportional to 10 EBR, which means that for this relation, for this reaction, we should have delta G bonding of 2 vacancies less than 0, meaning it should be a desirable reaction, it should energy is getting reduced. So, this is the system energy enthalpy is getting reduced, and therefore, this reaction should proceed forward. Now, let us see how many of these bonds, what will be the concentration of these die bonds or die vacancies. So, what is the delta HF? Like I said earlier, that will not go through the whole derivation, we will now look only at the formation energy. We know the if we can find out the formation energy, in this case it will be equal to 2 delta HF 1 V. This is not the right equation, because as we know that this should have a lower energy. Therefore, there is some term which must be reducing it, and that term is the bonding between these two. So, this is, let us denote this by H underscore H subscript V and superscript 2 V to denote that it is a die vacancy. So, there is a bonding between these two vacancies, and this is denoted by H under subscript B superscript 2 V, and this is the reducing term. So, the total delta H F 2 V is, as you can see, is less than 2 times delta H F 1 V, and once we have this, we can write the equation as, let me write it here, X 2 V equal to EXP this is without the formation entropy term. So, this is again the condensed form of the equation. You can always go back and expand those things now that you know the methodology to do that. Okay. So, this is the equilibrium concentration of die vacancies. Now, let me go back and try to find what will be the ratio of x 1 V by x 2 V. It is not very difficult, I have given you both the relation, you have to simply divide it. What was the x 1 V? X 1 V is equal to EXP minus delta HF. Let me, there is not enough space, so let me rewrite it by KBT, and for x 2 V we have again expressing it in terms of single vacancies formation energy, which is delta HF 1 V plus HB 2 V by KBT. Now, since these are exponential terms and we are dividing it, so it is as good as subtracting the term inside exponential over here. This term will get subtracted from the one on the numerator. So, this becomes so, this is the ratio of mono vacancies to die vacancies, assuming the system is in thermodynamic stable state. Mono vacancy by die vacancy. Now, what do we see here? Obviously, this term, which is delta HF 1 V, is greater, it would be greater by a big margin than this term HB2V. Hence, the fraction, this fraction that we have talked about, hence fraction x1V by x2V should decrease with increasing temperature. Meaning, as you become as you keep changing the temperature, the number of dye vacancies should increase, the proportion of the dye vacancies should increase with respect to mono vacancies. However, you must be careful that even at temperature as close to Tm, even at T approximately equal to Tm, the proportion may have increased with respect to room temperature or lower temperature, but still it is mostly the mono vacancies that dominate. So, it is mono vacancies dominate in percentage. To give you a rough idea, x1V would be approximately of the order of 10 to the power minus 4 to 10 to the power minus 3 at T approximately just little less than Tm, because we are not going into the liquid state, and mono vacancies concentration would be of the order of 10 to the power minus 6 to 10 to the power minus 5 at T approximately equal to Tm. What does this say? This says that x2V would be approximately 1% or lower of x1V. So, you can see that still it is the mono vacancies that will dominate. Okay, not, it is not that dye vacancies, the fraction is decreasing, so dye vacancies do not start to dominate. It is still a large fraction of mono vacancies that is present in the system. Okay, so now let us get to, now that we have seen mono vacancies, dye vacancies, now let us talk about vacancy aggregates. Let us say that you are using some non-equilibrium process like quenching. So, what happens in quenching? Somewhere at a very high temperature. So, high temperature you cool it rapidly to low temperature, that is quenching. So, over here the equilibrium concentration, which is an equilibrium, is high. Here an equilibrium should be low, but since you are cooling rapidly and the mobility of vacancies is not very large, that they can diffuse out to the nearby sink, and we can assume that there will be for most of them there will not be sink very close by available. What is a sink? We will come to that in a moment. Sinks for the time being we can assume that the sinks are the place where vacancies can go and merge, where they will disappear. So, here we can assume that no sinks nearby. So, just like sinks, there will also be sources from where if there is a place where vacancies can disappear. So, there can also be a place where vacancies can appear in a we are talking about a real system, real material. So, assume no sinks nearby. So, what will happen, that at lower temperature you will have, at this temperature you will have super saturation of vacancies. Meaning more vacancies than is allowed by thermodynamics, or more than what would be expected for a thermally equilibrium system. Now, here what happens is that in order to reduce the fraction of mono vacancies, what the system does to reduce the energy, because if there are lots of mono vacancies, the enthalpy is very high for the system. So, in order to reduce the energy of the system, how would the system reduce the mono vacancies? It forms, you guessed it right, it forms di vacancies, tri vacancies and clusters. So, when you have di vacancies and tri vacancies, as I showed you earlier, that when they form they come together, then they will have lower energy than independent vacancies, and therefore, the energy of the system gets reduced. So, that way you will have the system will be able to reduce the enthalpy or the overall energy of the system. So, now coming to the point that I talked earlier, sinks and sources. Inside a material, we are talking about increasing in the vacancy concentration with increasing temperature, or reducing of the vacancy concentration with reducing temperature. So, where do they appear, where do they disappear from? So, these are the places where they appear from are called sources, and the places where they disappear are called sinks. Now, here you may think these are some strange phenomena, but it is not like that, or not some very out of the world features. What we have are some simple components, the structural components of a material like surface. Now, what will happen, how can a surface generate or allow the formation or the act as a sink and source? Let us see. So, let us say this is a material, and like I said, so let us say I have this, I let this be a vacancy, and this is a simple two dimensional system that I am drawing here. So, here is your vacancy. Now, because vacancies can diffuse, so this vacancy can hop to this place, this hop to this place, and once it is here, then it is on the surface, and surface has already surface is already uneven, and even it can move to somewhere on the completely outside surface. So, it is as good as saying that we have vacancies over here, or and vacancies over here. So, this way this vacancy has disappeared onto the surface, or the other way round, this vacancy can hop into here, or this particular atom can move over here, and this vacancy can move over here, then it can move to here, then this can move to here. So, in this case the surface acted like, in this particular case it acted like a sink, in the second case it acted like a source, and which is actually the case for most of these structural units or the source and sinks. Most of them are act both as a source and also as a sink. So, this is a surface. So, surface is one example, free surface. Now, similarly, we have grain and phase boundaries. From your fundamental background in materials, you would know that there are regions with extended crystallinity, and they get interrupted by a region or a plane which is called grain boundaries, and if we have more than one phases, then this will be called a phase boundary. So, in the same drawing that I have shown you here, let me say that there is, so on to the other side. So, this is on this side you have, let us say the structure is very much, or the orientation is very much like that, but on this side let us say the orientation is like this. So, what we have here is this is a grain boundary. If it were between two different phases, then in that case it would be a phase boundary. So, the difference between grain boundary and phase boundary is primarily that one of them is differentiating or is a partition between orientation of two different materials or two different phases or of same phases. So, that way grain boundary is also called homophase boundary, meaning both the phases on both the sides are same, and a phase boundary is called a heterophase or the heterophase boundary, because on the two sides of the interphase boundary they are different phases. So, from this point of view there is not much difference. What we are particularly interested in is that when you have a boundary like this, what you see over here is that there are lots of empty spaces. Now, these empty spaces, what does that mean is that it is a potential site for vacancies to sit or vacancies to come out and get into the system. So, just like I showed you over here, these vacancies can actually from somewhere, let us say this is the vacancy, it can hop from here and over to here. So, it acts like a sink, or in the other case it can go from here to here and it will act like a source. So, this particular region where there is extra volume, this more free volume, this can act as both as a source and a sink. So, that is another region or another structure which allows for formation and degeneration of vacancies. Still another one is dislocation climb. So, we have a dislocation like this in a system, and I am not drawing the system around it. So, when it climbs, it moves up, what happens is that it leaves a trail of vacancies when it is climbing up. When it is moving down, then it absorbs these vacancies. So, these atoms come into this place and there is absorption of vacancies. So, let us say this is moving over here. So, whatever vacancies were in this particular region, they get formation of vacancies, and this is sink of vacancies. So, whatever vacancies are there, it gets into this region and it gets consumed. So, this is acting like a, when it is moving down, then this acts like a sink, and when it is moving up, it acts like a source. So, this is another source or another way that this vacancies are generated or consumed. Still another one is vacancy disks. So, inside a material you can have a disk made out of basically empty atoms. So, there is a region where there are no more atoms. So, around it is still all atoms. I am not trying to draw it here, just trying to give you a rough scheme of things. It is difficult to draw it here. It is just that there is missing atom over here. So, this is like a vacancy disk. So, now again if there are some vacancies, okay, now so I have almost drawn it. I thought I would not be able to draw, but okay. So, here the vacancy can move from here to here and over here. So, this becomes like a sink. On the other hand, because there is a vacancy, there is a large region, it can move on from here to here, and then it will becomes a source. So, again vacancy disks can become a source and sink. Similar to the vacancy disks, if this is a little larger, then we would call it micropores, and so this micropores which will act very similar to this can also act as source and sinks. So, now we have looked at the various places from where vacancies may appear and where they may disappear. Now, let us look at another aspect with relation in respect to vacancies, which is concentration measurement of vacancies. So, what we are trying to do here is characterize n by n, and assuming that it is being done in a thermally stable process in thermal equilibrium, then what we get is a equilibrium fraction. First method that we will discuss here is thermal expansion. Here let us say we take a rod and we heat it. So, let us say it is at low temperature and this is at higher temperature. So, there will obviously be an increase in the length. So, there is a delta L, actually what would change is delta V. So, the volume has increased. Now, this increase in volume can be attributed to two different aspects. One is the thermal expansion, meaning your lattice parameter has increased, and another is because of increase in vacancies. So, we can put this equation like this. This is the total increase delta V by V. Now, the thermal expansion, which is because of the increase in the lattice parameter. So, lattice parameter is one dimensional. So, in order to understand its effect in 3 dimension, we will have to multiply by 3, which is the approximate for the change in volume because of thermal expansion, delta A by A, and then n V by n, which is anyways a 3 dimensional. So, we do not need to multiply any factor over here. Now, this delta V by V can be written as 3 delta L by L equal to 3 delta A by A plus n V by n, or in other words, from here we can see that this relation becomes 3 delta L by L minus delta A by A. Now, this relation is giving us the concentration of vacancies from whatever temperature to temperature you have calculated the delta L, and for that you also need to calculate the delta A. So, we need to measure these two quantities, delta L and delta A. How can you do delta L? Simple optical measurement like a camera which is watching the increase in the length, because we have taken a rod. So, optical measurement can give you what will be the delta L. For delta A, it is a lattice parameter, and one of the best techniques to measure the change in the lattice parameter is X-ray diffraction. So, using these two techniques you can find delta L, delta A, and therefore, you will be able to find the change in the concentration of vacancies or the total increase in the volume because of vacancies. Now, with respect to that, let us look at one example. It is given that copper rod increases by 2% length. So, increases length by 2% when heated from 0 Kelvin to 1250 Kelvin. What fraction, now the question is what fraction of this increase is due to vacancies. What you are given is again the thermodynamic quantities delta HF 1V is equal to 120. Now, here it is given in joules per mole, and for that corresponding R can be taken as 8.314 joule per mole per Kelvin. So, what do you understand about the question? We already know something from earlier equation, which was that the total change in length, which is 3 delta L by L, is equal to 3 delta A by A plus NV by N. But what we are being asked is a fraction, which is this. So, the question is, what is this fraction of the total change? So, what you have to find is F equal, what is this F value, which is NV by N by 3 delta L by L. So, this is what you need to find. Okay. So, here NV by N is very simple. We have we just need to use the equation, and since we are only given delta HF, so we can ignore the entropy term. So, this is minus delta HF 1V by RT, okay, like I said, and 3 delta L by L. So, this is given 2%. So, delta L by L becomes 0.02. So, this is 1 over 3 into 0. Let me correct this, 1 EXP minus delta HF 1V by RT. Now, if you solve it, you would see that you are getting something like this, and I urge you to solve these problems, that the example problems, because these will form the basis of some of the assignments and maybe even the final exam. So, if you are able to solve this, then you can you would feel comfortable solving those questions. So, this is a fraction. So, the fraction would come out to 1 over 3 by 1 over 3 times 0.02. The whole of this fraction has to be multiplied by this exponential term, and when you solve it, you would get approximately 9.7 into 10 to the power minus 6, and we are talking about fraction. So, it is approximately equal to 1 into 10 to the power minus 5, or in other words 1 into 10 to the power minus 3%, which is how much? 0.001%. So, of the total increase in the length of this copper rod, when you go from 0 Kelvin to 1250 Kelvin, only 0.001% can be attributed to vacancies. Now, this is what we can relate back to when we said that density is a insensitive parameter, structure insensitive. Because you can see that even very close to melting point, you are not contributing much to the volume, which means the density would really not change because of the equilibrium concentration of vacancies. So, this is giving you, this example serves two purpose. It helps you understand how this method of thermal expansion can be used to find NV by N, and it is also giving you understanding that this total contribution of NV by N to the expansion is a very minuscule quantity, and therefore, we can term density as a structure insensitive parameter. So, we will come back in the next lecture with few more techniques to measure vacancy concentration. Thanks.